Welcome back. In this video, we're going to introduce our discussion of bearings and how we pick bearings based on the rated load and their rated life. So bearings are a little bit different of a component than other things we've looked at like shafts and gears, in that we aren't going to look for a factor of safety against fatigue wear. Instead, we're going to estimate a probability or a reliability that our part will continue to function. So this is a stochastic approach, a probabilistic approach. So for bearings, failure is probabilistic. When a bearing fails, what it means is that damage occurs in the rolling elements inside the bearing. So we're going to talk about ball bearings, we're going to talk about roller element bearings. And bearing failure is defined as when some amount of damage can be detected on the ball bearings themselves. So what happens is there's Hertzian stress, which leads to small deformations in the roller elements or the balls, and that will end up eventually flaking off, causing noise and debris inside the bearing, and usually bearings will be replaced before they completely fail, and so complete failure of a bearing is basically a noisy bearing, so they'll be replaced at that state. So we identify the bearing that we want for a particular level based on the life at that rated level that we want to get. So we're going to look at the load, the life, and the reliability. And all of these three things, the load, life, and reliability, work together to figure out what it is that we are looking for. So we are not going to be calculating a factor of safety. So when we discuss bearings, what we're going to be looking at is, for a particular type of bearing, how many failures do we expect to see over a given time period based on a particular load. So at the rated load, which we'll call C10, and we'll get back into these definitions in a little bit, we expect to get a point of the life where 10% of the bearings will have failed. So this is time, but really in terms of how many revolutions does our bearing take. So what this curve looks like is basically something like this. So out of the lot of 10,000 bearings, or however many we want to talk about, there is a point when, if we've loaded all of 10,000 of these bearings to a particular load, the rated load, there is a point at L10 where 10% will have failed. This load life is also calculated, it's actually calculated the opposite way. So for a batch, when 10% of them have failed at a particular load, that's how you identify what the particular load rating is. But it's equivalent way to think of it either way. So instead we set it at a particular number of cycles, which is 1,000,000 inner cycles, and identify a C10 from that. Now, if we do that, what we imply here from a catalog rating is that we are confident that if we pick a bearing that we want to run at the rated load C10 load for a rated life, then we have a 90% confidence that that bearing will still be working. If we want a higher confidence, then we need to pick a higher rated load, or a bearing that can last a little longer. All right, so let's get into these definitions a little bit more specifically. So L10, the rated life, is the number of cycles such that 10% of the bearings will fail at that C10 loading, or the rated loading. And we'll talk about the rated loading in a moment. So every bearing manufacturer can make their own and decide what their base life is. But for most of the examples in the book, we will set this at 1,000,000 cycles. And specifically, we mean 1,000,000 cycles of the inner ring. All right, now let's look at C10. So C10 is the theoretical load on a bearing where after the L10 number of cycles, which we'll again call 1,000,000 cycles, of the inner raceway, the inner ring, 90% will still be running. So that is what we mean when we say the catalog rating. So 90% will not be exhibiting those signs of failures. We also call this the catalog load or the basic dynamic load. So let's begin with the simple case, which is just radial loading. So, for example, we've looked at this beam before, where we put a force in, and we assume there's some reactions at these bearings. And we found what these reactions are. Well, now we're going to be looking at how those reactions relate to the type of bearing that we need to select. So we know we're going to have some reactions that we can find out from statics, and we will be able to pick out what simple bearings we need from that. So alternatively, we might have axial forces as well. Those are going to be called thrust loads. And when we have both thrust and radial loads, we'll have a slightly more complicated way of specifying our bearings. All right. To find the life that you would expect to get out of a product, we compare the load it's at to the load we want to get. So what this equation says is that the life that we'll actually get out of a particular bearing is related to both its catalog life and its catalog load. So F is the actual radial load that our object is under. C10 is the catalog load, and we raise that to the A, where A is either 3 for ball bearings or 10/3 for roller bearings. And then multiply that times the rated life. So the fraction of the load capacity raised to the A, multiply that times the rated life in order to find the actual life that we're going to get. So that is, assuming we know the rated catalog load and we know the forces, how long will this bearing last? So if we're asking ourselves, I've got a particular bearing and I want to know how long it will last, this is the way to approach it. If instead we know the load that we have and we know the forces acting on our system, we may instead want to find which bearing do we need. So to find a C10 that's appropriate, we're going to use the load times the ratio of the life we want over the rated life raised to the 1 over A. And you'll see that these are basically the same equation. Simply solved one for the other. And again, A equals 3 or A equals 10/3. So let's see how this works with a simple example. So let's select a bearing first of all. If we're selecting a bearing, that means we're going to try to find a C10 for our particular situation. And we'll select a bearing knowing that our desired load is 5.5 kilonewtons. That is the reaction load that we found. And we know that we want a desired life in hours of 5,000 hours of operation at 300 RPM. We're going to look for a deep groove ball bearing that will fit our selection. So we're going to end up looking in the table 11.2 for this. This table 11.2 is based on a catalog of ball bearings. You can, of course, look for SKF for any other catalog out there, and you'll see different rated loads. The process and the nomenclature may be a little bit different, but what you're doing will be the same. So first of all, we need to figure out what is the life that we want to get out of this thing. It's not going to need to be in hours, it's going to need to be in revolutions. So the life is 5,000 hours multiplied times 300 revolutions per minute multiplied times 60 minutes in an hour. That gets rid of everything except the revolutions, which is the number of revolutions we'd like to see. That is equivalent to a life of 90 million cycles, 90 times 10 to the 6 revolutions. And recall that we said our rated life for the particular catalog that we're looking at, L10, our catalog rating, is set at 1,000,000 cycles, or revolutions. So following that framework that we had before, we have the rated load that we're looking for is 5.5 kilonewtons multiplied times our desired life, which is 90 million revolutions, divided by 1,000,000 revolutions, raised to the 1 over A, where A in this situation is 3 if we're using ball bearings, 10 over 3 if we're using ruler bearings. So if we work that out, we find that we are looking for a catalog loading of approximately 24.64 kilonewtons. We can find one that's pretty close. So let's look at that catalog. So based on table 11.2, we can look for a rated load for our particular operation. So we are looking for deep groove ball bearings because we don't need the thrust load capabilities of angular contact bearings. Instead, we just need to look at the single row deep groove ball bearings, which is this 02 series, and find a load that will work for us. So 24.64. So going down the list, we find 25.5, which gives a bore diameter of 35. We'll specify the bearing that we're interested in as a 35 millimeter bore deep groove ball bearing. So that worked out well for finding out, given a particular load and a life that we want to get, a catalog bearing that will meet our needs. Now, alternatively, what would happen if we had a bearing in place and we wanted to know what type of life we would expect to get out of it? So let's try it this way. So instead, let's look at a system where we have that same load of 5.5 kilonewtons, and instead we see that the bearings that are on this shaft are a 25 millimeter bore deep groove ball bearing that's from this catalog that we have a nice table for. So what we can do is we can use the information in our catalog to tell us what type of life should we expect to get out of this type of bearing, and does that meet our needs? So the 25 millimeter bore diameter right here and deep groove ball bearings gets us a 14.0 kilonewton rated load. So our C10 is 14.0 kilonewtons. That means the life we should expect is the rated life times the ratio of the C10 over our actual loading raised to the A, where again A equals 3 because we're dealing with ball bearings. So from our numbers, that is L equals 1 times 10 to the 6 cycles for our rated system, a 14.0 rated load compared to the 5.5 kilonewtons load that we're actually at, raised to the 3. This says that we should expect to see about 16.5 times 10 to the 6 revolutions of life for our bearings. Now, how long is that in hours? Well, that of course depends on speed. And it can be difficult to interpret speed in revolutions per minute or hours without considering just exactly how many minutes there are in a day and how many hours there are in a work week and so forth. Alright, that'll about do it for this video. In the next video, we'll discuss what if we don't want to have 90% certainty, but instead we want to have a higher or even a lower reliability. And we'll look at a reliability-based approach to specifying the bearings. Until next time.